Dear students, in this video we are going to study diphenylmethane. We will see structure, synthesis, reactions and finally applications. We will also look at what are engineering polymers. So let's get started. Diphenylmethane is slightly different than the compounds we have seen earlier. We have studied naphthalene, then anthracene and phenanthrene. If you look at classification of polycyclic hydrocarbons or polynuclear aromatic hydrocarbons, they are classified as benzene derivatives, that is benzenoid, and non-benzenoid. So here you can quickly notice it is a 7-membered ring fused with a 5-membered ring, so it is not containing benzene, which is a 6-membered ring. So benzenoid are further classified as isolated and fused rings. We have already seen fused compounds, so naphthalene and anthracene, because all rings are joined in a series. They come under linear, while in phenanthrene, third ring is joined angular. It is not in the straight line. So that is about phenanthrene. Diphenylmethane, as well as the next member, triphenylmethane, this biphenyl, they all come under isolated, because you can see two benzene rings, they don't have any carbon common in them. There is a bond joining them. But here if you see, two carbons are common in every case. Here also two carbons are common. Here also these two carbons are common. So when two rings are isolated, when they don't share any carbon in common, they fall under isolated category. And in between them, we may have another carbon also, like diphenylmethane. So still they are isolated because two rings are separate from each other. Let's look at the structure. It consists of 13 carbon atoms and 12 hydrogen atoms. So out of 13, 12 carbon atoms are because of two phenyl rings, 6 carbons each. And central is the methane. If you see the common name diphenylmethane, it starts with parent as a methane. So central carbon is considered as a methane over here because carbon's valency is 4. Two hydrogens are replaced by these two phenyl rings, and this carbon is still carrying two hydrogens, so it is CH2. If you look at IUPAC name, the main root is considered as dibenzene, so it starts with benzene. So on benzene you need to consider this methylene group as a branch, so you will number benzene, you will start numbering from the carbon which is holding this CH2 group. Both rings will be numbered as 1 to 6. Just to distinguish between them, any one ring will be considered as 1, 2, 3, 4, 5, 6. It will be numbered as this, while another will be numbered as 1 dash, 2 dash, 3 dash, likewise up to 6 dash. So first number is given to the carbon which is holding this central methylene group. So it is 1 dash methylene dibenzene. It will just help if we have substitutions. Suppose here we have methyl group and here also if we have methyl group, then it will become 3,5 dash dimethyl methylene dibenzene. It is a white solid but melting point is too low, so at room temperature also it will exist as a liquid. Molecular weight is 168. So there is nothing much about to be told in the structure because two benzene rings are intact. Unless they are substituted, they will show resonance as like simple benzene. Benzene has two resonating structures, so this will also show two resonating structures per ring. Let's talk about a synthesis. There are various methods by which we can get diphenylmethane. So every time you need to see whether reactants are containing two benzene rings as well as central carbon. So Friedel-Crafts alkylation and even Friedel-Crafts acylation. These are common reactions. You can react benzyl chloride. So it is containing benzene ring CH2Cl. So one reactant is having benzene ring plus carbon. So you can simply treat it with benzene. In presence of Lewis acid, upon slight heating, there will be elimination of HCl, hydrogen from here and Cl. Elimination of HCl can give us diphenylmethane. Similarly, we can take benzoyl chloride. So benzoyl chloride now consists of benzene ring and COCl. So when you react it with benzene, there will be formation of benzophenone first. And after reduction of this, loss of oxygen, addition of two hydrogens can give us diphenylmethane. So though benzophenone was intermediate in the earlier reaction, benzophenone is easily available as the starting material. So upon reduction of benzophenone, we have seen we can get diphenylmethane. So for reduction, now we need some agent. There are two popular reactions for reduction of ketone compounds into methylene. First reaction is Wolff-Kishner reduction. So this is famous for reduction of keto groups. Here, such ketones having any R group, they are reacted with hydrazine. So upon reaction, you can see it is a reduction, so there is loss of oxygen. And we get oxime-like compound over here. So oxygens, there is elimination of H2 and this O. So oxygen's place is taken up by nitrogen. So these two R groups, then there is C double bond N. If we have OH over here, we call it as oxime. So here we get this intermediate which upon hydrolysis with alkali can give rise to formation of methylene group in place of nitrogen. There are several modifications of this Wolff-Kishner reduction that if we carry out reaction in presence of potassium tertiary butoxide, then replacing this glycol with a DMSO or using protic solvents, then reaction can be made to happen at room temperature. Otherwise, reaction needs heating and reaction is very slow. So making these changes, different research groups, they have tried increasing rate of reaction. Another alternative for carrying out a reduction of benzophenone is use of zinc amalgam as a catalyst and some acid. Now, original Clemmensen reduction involves very harsh acidic conditions. So, it is usually not preferred in case of ketones which are susceptible or sensitive to the acids. So, if you want to convert benzophenone by Clemmensen reduction, harsh acidic conditions, one research group have tried. If you can replace it with glacial acetic acid, then it is possible to get diphenylmethane in good yields. Otherwise, Clemmensen reduction takes place in presence of a very strong acid like HCl, H2SO4. So if a reactant is not stable to it, such reagents will decompose it. It is also possible to get diphenylmethane by help of Grignard reaction. So benzene magnesium bromide, if we treat it with benzyl bromide, these are reaction conditions. By keeping them in minus 20 degrees Celsius, tetrahydrofuran as a solvent, ferrous as the catalyst, diphenylmethane can be synthesized. There is loss of MgBr2, which act as a good leaving group. There is also one option to get it from two benzene rings. So as we have two benzene rings out here, we just need central carbon. So central carbon can be provided by formaldehyde, which upon heating in acidic condition can give us diphenylmethane. There is loss of water. So now let's move on to reactions of diphenylmethane. Diphenylmethane, because of presence of the central methylene group, it shows acidic behavior. So it can easily form carbanion by loss of proton, and it will easily react with bases. So it can react with sodium in the form of, say, sodium amine to give us substituted compound or sodium salt of diphenyl methane. This reaction is actually carried out in order to get a substitution of any alkyl group on the central methylene, because once we have this sodium substituted compound, if you react it with any alkyl halide like CH3Br, so there will occur replacement type of reaction. There will be loss of NaBr and R can take place of Na. So this alkylation is made possible because of acidic nature of this methylene group. It is made to react with the base, and then later on base can combine with halogen so that we can get the counterpart. This R alkyl group can be added to the central methylene group. With respect to electrophilic substitution reaction, there is some different behavior seen. That is, in case of nitration. Nitration happens at the ring because NO2 as electrophile, benzene ring is electron rich. So initially one ring at para position will get nitrated. If we still continue, then next another ring with para position will also get nitrated. So it will be bis 4-nitrophenyl methane. But in case of bromination, it has been observed that bromination takes place at the central methylene group and not at the ring. And because it is in presence of light, it is supposed to be a free radical reaction, and the central carbon is more prone to form a radical, and it will accept bromide to form diphenyl methyl bromide. As we have already seen, we can obtain diphenyl methane upon reduction of benzophenone. So reverse is also true. Diphenyl methane upon oxidation with any strong oxidizing agent like potassium dichromate in acidic medium or elemental oxygen, it is possible to oxidize this central methylene group. There will be loss of hydrogens and addition of oxygen. So diphenyl methane upon oxidation gives benzophenone. Last reaction is ring formation via dehydrogenation. So in this reaction also dehydrogenation takes place, but that is from central methylene group. If you pass diphenyl methane from the red hot tube having a temperature 450 degrees Celsius, then there is loss of hydrogens from these two carbon atoms, and there will be a bridge formation which can lead to completion of the ring at the center. This compound is known as fluorine. So there is dehydrogenation, because of which ring formation is attempted and we get a tricyclic compound. Coming to the applications, if you see general uses, diphenyl methane has been used in synthesis of luminogens. Now what are luminogens? These are the substances which are used to induce emission in other substances. Other means such drugs or anything which you want to detect, any compound which itself is not able to get detected by absorption or emission of the light. So luminogens help such compounds to get detected by imparting extensive electronic conjugation which can help in emission of the light, and this emitted light can be measured. So diphenylmethane consists of two benzene rings, so there are a lot of pi electrons and conjugation. So if you prepare a higher derivative of it which can act as a luminogen, it will help to produce light. Then another application is preparation of polymerization initiator. This is the simple compound DPMK, wherein central carbon which was holding two hydrogens, out of that one is replaced with potassium. Even we have seen in the reaction it can be replaced with sodium also, because it is acidic you can react it with any alkali metal. Now this metal can act as a trigger. It can initiate polymerization reaction, so it can get removed and we can add any other group which we want. So we have seen this in the alkylation reaction. Synthesis of dendrimeric polycyclic aromatic hydrocarbons. So this is the substance. This is the chemical name given. This is synthesized from diphenyl methane and it is used in synthesis of dendrimers. Dendrimers are macromolecules which are used nowadays. A lot of research is going on them. They are used to carry the drug. So as a drug delivery system, they are now in use. There also diphenylmethane finds use. Then some other general applications are as a perfume, as a solvent, as a pesticide, that also exist. What are engineering polymers? These are derivatives of diphenylmethane. See, we have example of polycarbonate wherein central two hydrogens, they are replaced by methyl groups. Even substitutions can be there at para positions. Here it is carboxylate, ether. In polyether sulfone, we have central carbon removed and we have oxygen there. At para position, we have sulfone group. So this is polyether sulfone, or we can have polysulfone, which is a combination of these two. So such polymers containing polycarbonate, polyether sulfone, polysulfone, and extended structures, because they are polymers, so there will be a lot of such monomers which will join to each other to form longer chain compounds. But these polymers, they are having extremely higher strength, so high melting points and high impact strength. So they are called as engineering polymers. Main skeleton is diphenylmethane and we carry out substitutions at the central carbon as well as para carbons of the phenyl rings. Besides this, diphenylmethane can also be used in synthesis of dyes like auramine O, auramine G. This is the structure of auramine O, wherein you can see phenyl rings are there, central carbon, two hydrogens are gone, and we have a double bond NH over here. At both para positions, there are substitutions of dimethyl amino. So usually such indicators are prepared as salts, say hydrochloride salt, because here we have imine-like structure. So acidic salt is prepared to increase their solubility. Similarly, we have Mischler's base. Now this is used in the production of several dyes and it itself can act as an reagent for determination of some metals like lead. So this is a simple structure of diphenylmethane wherein at both para positions you can see dimethyl amino group. These two structures are same, just in auramine O we have substitution at the central methylene also. All the medicinal applications of diphenylmethane are in the form of Benzhydryl compounds. Now these are the compounds which are having parent structure as diphenylmethane. So you can see two phenyl rings over here and this was the central methylene group. So either substitution is done on the rings or this central methylene group. So here you can see one hydrogen is replaced because of this group to make it diphenhydramine. This central carbon can also be extended. It can be also a part of a chain which ultimately forms a different ring over here, or it can form a fused ring over here. So anyhow, either as a substitution or bridge, this carbon will be reacted. Diphenhydramine is a popular antihistaminic which is used to treat allergies. There are some other applications also. Few other benzhydryl compounds indicate fexofenadine, which is also antihistaminic, predinol, which is a muscle relaxant, sertraline is an antidepressant, cyclizine is used in nausea, modafinil is used in sleep disorders, loxapine, olanzapine, they are used in treatment of schizophrenia. These all were synthetic drugs. There are some naturally occurring compounds which also show multiple actions like bromophenol. So here you can see bromophenol, two benzene rings are there. There are four bromide substitutions. Rest four are phenolic or hydroxy substitutions. Central methylene is intact. This bromophenol is tyrosine phosphatase inhibitor, and it is currently under investigation whether it can be used in prevention and treatment of diabetes mellitus and obesity. There is anti-cancer drug tamoxifen. Here you can see there are three phenyl rings. So you can quickly make out these are two phenyl rings because this is the central methylene group. Now this methylene group has been reacted to have a substitution, as well as there is another ring over here. Even benzene ring is substituted. So this is a benzhydryl compound. Tamoxifen is used as an anti-cancer agent. So this is all about diphenylmethane. These are a few references. You can go through it. Next in this series is going to come triphenylmethane. So until then, take care. Goodbye.